Good afternoon, everyone. Today I'll be presenting my talk titled Chemistry Modeling of the Solar Coronal Dynamics with an initial non-force free magnetic field. So this work has been done in collaboration with Dr. Amit Bhattacharya and Dr. Sanjay Kumar at the Udaipur Solar Observatory in India. So the following is the outline of a talk. Uh, I'll be starting with the motivation and algorithm for the work, and then I'll be discussing non-force free magnetic field and why they should be applicable for coronal magnetic fields. And then I'll be discussing results from a analytical non-force free extrapolation and MHD simulation for active region 11283. And finally, I'll be showing some preliminary results for a numerical non-force free extrapolation and simulation for active region 12192. So this is the motivation for the talk. We know that coronal loops are highly dynamic, as can be seen in this AIA 171 movie of a solar flare for this event, X 2.1 flare that occurred on 2001 September 6. And we know that coronal plasma is highly non-diffusive, which means it is infinitely conducting. And under such situations, the magnetic field lines are known to be tied to the fluid plasma, so which is also known as the flux freezing condition. So, in order to understand the dynamics of the magnetic field line, understanding the dynamics of the magnetic field line is very important in understanding high energy events like solar flares and CMEs. So, I'll just present the algorithm for the work first. So, basically, we do not have information of the coronal magnetic field. What we do have is photospheric vector magnetograms. So, we obtain such magnetograms from observations prior to a high energetic event like X-class solar flare, and then we use a model, in this case a non-force free magnetic field, to extrapolate the magnetic field for the entire coronal volume. Here this is done by first finding an analytical solution for the non-force free magnetic field and then correlating with the observed magnetogram. Finally, once we have the input for the entire coronal magnetic field, we can use it in a MHD code to simulate in more detail. So as I said before, there are no magnetogram with high spatial and temporal cadence are routinely available from space-based MI. So we can easily obtain a magnetogram of an active region prior to an X-class flare. So that can be set up as an initial field. Now it should be noted that for example, in this case, this is a line of sight magnetogram of an active region where the white represents the positive polarity and the black represents the negative polarity. So now the information of the three components of the magnetic field are only known on a two-dimensional surface of the photosphere and not the entire coronal volume. So in order to infer the magnetic field in the entire coronal volume, there have been various numerical extrapolation techniques that has been used. For example, this is a simple potential field extrapolation technique uh, by which we can generate the magnetic field in the entire coronal volume. And there are other techniques also, for example, nonlinear force free field extrapolation. But these numerical techniques have certain issues. For example, unavailability of the boundary condition. So from observations, we know the magnetic field only on the lower boundary, which is the photosphere. And for our extrapolation, we always have to assume some boundary conditions for the side and top surfaces. Further, there are uncertainties in the measurement of magnetic field in the photosphere itself. Then, in order to extrapolate for the coronal magnetic field, we have to make an assumption for the equation of state for the magnetic field. For example, we can take a linear force free field, a non-linear force free field, or a non-force free field. Now, in all these cases, there are also numerical constraints in maintaining the divergence free condition for the magnetic field. So, these problems motivate us to look for solutions of the coronal magnetic field within the analytical domain itself. In order to do that, we first look at the equation of the state. So generally, there are two equations of state for the coronal magnetic field which are used quite. One being the force-free fields and another the non-force-free fields. The motivation for the force-free fields comes from the theory of Taylor relaxation, which says that an infinitely conducting single fluid plasma undergoes a viscous dissipation in which it minimizes the total energy, keeping the magnetic helicity constant. So the equation for force-free fields is given by this equation, del cross B equal alpha B, where alpha can be a constant or a function of space. This alpha is also known as the force-free parameter or the twist parameter because it also represents the number of twists in a magnetic field line per unit length. So it can be easily seen that the Lorentz force J cross B is 0 for these fields, hence the name force-free fields. Now for externally driven systems like the photospheric plasma, a non-force-free assumption is actually more viable. And the motivation for non-force-free fields comes from this minimum dissipation rate principle, which says that a two-fluid plasma under an external drive will try to dissipate, minimizing the total ohmic plus viscous dissipation rate, and at the same time keeping the general helicity conserved, which means the fluid as well as the magnetic helicity conserved. So under such situations, we obtain a general solution for the non-force-free field, which can be written as a linear combination of two linearly force-free fields. So here B1 and B2 are two linear force-free fields with different values of alpha. So now from observations we know that the photosphere is non-force-free. So hence we look at these non-force-free fields in greater detail. So as I mentioned before, if B is a non-force-free field, it can be written in a general case as a linear combination of two linear force-free fields, and the solutions for linear force-free fields are well known. These are the Chandrasekhar-Kendall solutions, which in spherical polar coordinates can be written in this form. Here, the flux function psi satisfies the Helmholtz equation, which is given by this equation, and the expression for various components of the B can be written in these forms. Now, the solution for psi takes this form, where it should be noted that the radial function now is written as a linear combination of both Bessel J and Y, and we have constructed it such that the outer boundary R1 of a spherical shell is a flux surface, such that all the field lines are contained within a shell of radius R1. This has been done so that the total energy for the linear force-free field are finite. Also, it should be noted that this parameter alpha determines the number of modes or the oscillation that we will get in the radial direction. So, yeah. Yeah. No, so these are linear force-free fields. So alpha is constant. Yes. So I'm combining two linear force-free fields with slightly different values of alpha, such that the net Lorentz force is non-zero. So that gives me a general non-force-free field. Yeah.
Just a clarification, and is your psi and curl operators non-dimensionalized? Because you have the toroidal and colloidal as the same string function, but there's one has there's a 1 over r difference in their dimensionality. There's a curl versus a curl.
This is alpha, I think.
The line 2.
There should be two different sides on what I thought.
Yeah, if they're dimensional, then those two terms have different dimensions. But have you non-dimensionalized them somehow?
Okay, I'll check that.
Yeah, if it's force free, maybe they are the same. But there has to be a dimensional factor.
Yeah, so alpha has a dimension of 1 over length. So, so I think that should.
This is another class, sorry.
Yeah.
So this is linear combination of two
Linear force-free fields.
constant alpha force fields. So this is a subset of measure 0 of the possible number of non-force free magnetic fields. Is that right?
So no, there is no constraint that has been put on the North. So in any general non-force field can be decomposed into a combination of two linear force fields. That's it.
Who discovered that?
I think it was in. Okay, I'm not sure of that. So it was in this paper. Uh, but there were other papers also where you had extra. You can add a potential field also, and it will still remain. So this is the domain of calculation for magnetic field. So as mentioned, so we have a outer shell of radius r1, which has been constructed to be a flux surface, such that all magnetic fields are contained within this spherical shell. Just to clarify, this is a localized spherical region and not the entire sun. So it is somewhere close to the surface of the photosphere. And also it should be noted that in the radial part of psi, we had both Bessel J and Bessel Y. So we have to avoid the origin to so that there is no singularity at the origin. So we take a inner boundary also of radius r naught. So the solutions that we are the magnetic field that we are defining is in this region between a shell of r naught to r1. So we can solve for the magnetic field in this spherical shell. So for example, as an example, I have shown one meridional cross section of one particular mode of the linear force free field, where all the field lines are contained within a particular shell. Now, in order to compare these solutions with the observed magnetogram, we define a local Cartesian volume gamma over here, such that the lower boundary of this Cartesian plane now mimics a photosphere. So the magnetic field that we obtain on this lower boundary will act as a template for my magnetogram. Now the radius at which I place this parallelepiped r prime, that can be varied. Also the direction of the normal to this plane, that can be varied by this angles theta prime and psi. So we have a bunch of parameters, this r prime, theta, psi, as well as the particular mode of the Chandrasekhar Kendall's. So by varying all these various parameters, I can get a large number of template magnetograms that can be then compared with the observed magnetogram to obtain a best fit non-force free analytical solution. So here I show one such example. So what we have on the left is the actual observed magnetogram that we obtained from HMI. This shows an active region uh, just prior to a flare, and this is the best fit magnetogram that we were able to obtain from the analytical non-force free solutions. So in order to define a correlation, we define a parameter here, which is essentially nothing but the dot product of the magnetic field of the observed and the analytical solution, weighted by the strength of the observed magnetic field. So this varies between 0 to 1. So 1 would give a perfect correlation, 0 will give no correlation. And in this case, we were able to get a correlation about 0.6. So we notice that we are able to capture the large scale feature of the observed field, but we miss the small scale features. So keeping this in mind, so now we have obtained the entire three-dimensional magnetic field in that Cartesian volume, and this can be taken as an input to the MHD code in order to go look for the dynamics of the magnetic field. So before I show you the solutions of the simulations, I wanted to point out some important features of the initial non-force free magnetic field. So as I mentioned before, we were able to capture the large scale features of the magnetic field. Like here we see that there is predominantly a dipolar geometry with a stronger negative pole, and then we see these twisted field lines that join the main polarities, and they have this sigmoid like structure which is also seen in the UV images of the active region. and then there are also this some weaker polarities that are present in the system. So another important feature in the initial magnetic field topology is this presence of X-type null lines. There are two X-type null lines here, X1 and X2. By X-type null lines, I mean like there this line uh, such that at each point along this line, if we draw magnetic field lines in their vicinity, they will have this two-dimensional X-type null-like geometry. So, and this can be seen in this side view and top view of this initial magnetic field. So, what is important about these X-type null lines is that they are preferred location for magnetic reconnections. So, to draw these field lines, what we have done is we have drawn isosurfaces of almost zero magnetic field strength along in the entire computational domain, and we have obtained only these two X-type null lines. Another important feature in the initial magnetic field was presence of flux ropes. So by flux rope, I mean magnetic flux surface, which is comprised of twisted magnetic field lines. So there were like these four flux ropes that were present in this initial field. So this red flux rope is overlying the central polarity inversion line. So actually we would look at the dynamics of this flux rope in more detail in the simulation. It should also be noted that these flux surfaces are coaxially nested surfaces, and we'll show, I'll come to that point later. And in order to show how much the flux rope is twisted, I have shown this uh, the color coding with the seed points. So we can see that the flux rope has taken about a 180-degree twist as it goes from one end to the other. Also, in order to note the distribution of the Lorentz force in the initial non-force free magnetic field, we can look at these two figures. The left panel shows the histogram of the ratio of the magnitude of the Lorentz force with the gradient of the magnetic pressure. So we can see that the field is essentially non-force free. But if you look at the spatial distribution of the Lorentz force, we can see that the Lorentz force decreases as we go up in the height, which would mean that the lower boundary is more non-force free. But if you go for upper layers in the atmosphere, they become very close to the force free state. So given this, now in order to study the temporal evolution of the initial magnetic field, we use these magnetic MHD equations, which are these four set of equations. The first equation is nothing but the momentum balance equation. The second one gives the incompressibility condition. The third is the induction equation for the evolution of magnetic field with an infinite electrical conductivity. And the fourth one is the divergence free condition. So to summarize, what we are doing here is viscous relaxation of a thermally homogeneous incompressible magnetic fluid with infinite electrical conductivity and initial non-force free magnetic field. So in these simulations, we do not provide any initial flow also. So the flow is generated because of the initial Lorentz force in the system. So the flows are generated spontaneously, not prescribed. Also, the physical parameters are scaled in the following manner: the magnetic field by the strength of the mean field, velocity by the Alfvén velocity, length by the length of the magnetogram itself, and time with respect to the Alfvén time scale. And this tau nu is a viscous dissipation time scale. So these equations are implemented numerically through this Euler MHD code. So here I show the evolution of the central flux rope. So what is shown here is the top and side view of snapshots of the evolution of the magnetic field at different times. So here we have this dipolar geometry, and I have drawn two sets of field lines. One is this white field lines, which are the overlying field lines which can be seen here also. These are the high overlying field lines joining the two strong polarities, and then we have an underlying this low lying flux rope, which is like hovering over the main polarity inversion line. And I have also drawn these two X-type null lines here. So what we see is that as time progresses, the overlying field lines, the flow is generated such that due to the initial Lorentz force, that the overlying field lines move very close to this X-type null line, and as soon as they hit the X-type null line, they bifurcate and they reconnect. So as these overlying field lines are reconnecting, they're actually moving and creating a gap in this central region. So this creates a decrease in magnetic pressure and magnetic tension over this low-lying flux rope. So because of this decrease in the magnetic pressure, this flux rope rises, and after some time, even this is pushed towards this X-type null line due to the flow, and then even this flux rope goes and reconnects. So I had drawn the flux rope as coaxial nested surfaces. So as soon as the outer surface reconnects, I remove that and I show the inner surface, so that we can see that the flux rope is reconnecting successively in time. And the simulation is stopped when the flux rope loses its structure. So we can see that as the overlying field lines are moved, this flux, the height of this loop increases, and then it reaches this X-type null line, and then this also shows a bifurcation. So actually, we had an infinite connecting plasma to begin with, but whenever we reach this subgrid scales, there is this algorithm for MP data, which sort of mimics magnetic reconnection through numerical resistivity. So
On the previous view graph, you have a set of equations, but you've got a P in a row. So do you have some perfect gas? And then do you have an energy equation? Or?
so it's actually an incompressible homogeneous fluid. So the temperature is it's isothermal, so we don't need. So and as you said, like so we don't have a physical resistivity, but whenever we get reach subgrid scales, we mimic reconnection through numerical resistivity.
You know, I mean, clearly that's important for the dynamics in
Yeah.
the first equation. So you've got an effective diffusivity up there.
Yeah. So what we are
And it's compared with del squared V. How
So-
big is it compared with the diffusion you have in the plasma?
so that is said by this time scale of so we have this alpha and this viscous dissipation time scale. So and this ratio in this case is about 10 power minus 3. Whereas if you put the actual numbers for the corona, we get something like 10 power minus 5. So we are not able to reach the actual numbers which are there in the corona. But I guess what that means would be like since the time scale is scale with respect to the alpha time scale, what we have is the dynamics would be sped up by a factor of 100 or something. So every 10 second here would mean 1,000-second time scale, assuming everything else remains same. So yeah, so I'm just showing the movie of the same thing. So we see that first the overlying field lines reach this X-type null lines, they reconnect, and then we see that they move out and clear out the region in the middle. So this decreases the magnetic pressure in the middle, and that allows the flux rope to rise. And this can be seen even more clearly here. So we can see that the ascent of the flux rope, and as it reaches this X-type null line, then it sort of bifurcates. So we were able to capture two important things. One is this rise of a flux rope, and secondly the bifurcation. Now we did notice that all the reconnections are taking place at one of the X-type null lines and not the other. So to answer like why all the reconnections are taking place at x2 and not x1, we draw the streamlines of velocity in vicinity of these two x-type null lines. So we see that at one of the x-type null lines, all the field lines are actually almost parallel to each other. So hence this configuration is not very conducive to magnetic reconnection. Whereas the field lines on the other x2 null line, we see that this is pulling oppositely directed field lines very close to each other. So this is a very favorable conditions for magnetic reconnection. So hence we see that all the reconnections are taking place at this x2 null line and not the other one. So this gives a asymmetric nature to the flow. Also, a similar bifurcation of the flux rope for the same active region was observed in 304 angstrom channel of AIA, and so we were reasonably able to fit this in our simulation. So this sort of gives some credibility to this using analytical non-force free field for simulating such active regions.
So when you say
Yeah.
fit, you mean that you could find something that looked like that, have that place in your simulation.
Yes.
You didn't adjust any funding parameters to make it fit your calculation, it just naturally arose.
The initial magnetic field, you mean? Or?
I'm asking about this particular.
So this is not.
It's not a. You haven't fiddled with some knobs to make it fit. You just started from an initial position, let it run, and it produced this.
Right. So like we are not giving an initial flow that should produce the reconnection. So in some sense what we are doing is we are fitting the magnetic field line as well as the initial Lorentz force in the system by using a non-force free initial. So we are hoping that we are capturing the initial field as well as the initial force, so that the flow is generated spontaneously, and that should lead to the correct dynamics if you are able to capture all the parameters properly. So I'll summarize this first part. So we were able to obtain analytical solutions of non-force free magnetic field, which shows good correlation with observed topologies of coronal magnetic field, which were used as initial field for MHD simulation. In our simulations, we are able to capture asymmetric rise and a bifurcation of a flux rope. However, we failed to capture the subsequent X-class flare, so which would show up as a impulsive ascent of the flux rope, which was not present in the simulations. And we attribute this flare failure to not accounting for the flux emergence that took place, because the initial field was taken in this case 1.5 hours before the actual flare took place, and there was lot of flux emergence that took place just 10-15 minutes before the flare. And our boundary conditions, so what we are doing is the initial value problem, and it does not account for anything if the boundaries are changing in between. So so we cannot capture this extra flare. Another problem with using analytical solutions are that we can capture only the large scale features of the magnetic field, but we do not have the small scale features that are present in the magnetogram. So in order to address this issue, so we looked at another X-class flare event in a case where there was not much flux emergence preceding a X-class flare. So the active region we chose was this AR 12192. So this was the largest sunspot group and the most prolific flare producing site for the cycle 24. So what we're looking at is one particular X 3.1 flare which was non-eruptive. That means it didn't produce any CMEs. And here I have shown the positive and negative flux emergence at the lower boundary as a function of time. So we see that during the flare and afterwards, there was not much flux emergence. So this is a particular good choice for our simulations. And like here I'm playing a movie of the normal component of the magnetic field, and we can see that the bottom boundary is not at all evolving during the entire period. Also, we saw this X3.1 flare in this 171 angstrom movie, and we can see that the flaring site is somewhere near this region. I'll come to that point. So, in order to capture the small scale features in the magnetic field, this time we did a numerical non-force free extrapolation, which was again based on this minimum dissipation rate principle. So, to remind us, this minimum dissipation rate principle says that system will spontaneously evolve to state which will minimize both the ohmic and viscous dissipation rate, and that will lead to a general non-force free solution, which is a superposition of two linearly force free fields. Now, in this case, each of the linear force free field is numerically extrapolated from the bottom boundary by using just the normal component of the magnetic field by a method which is based on this fast Fourier transform algorithm. And this alpha parameters are determined by minimizing the deviation between the numerically computed and the measured transverse components of the magnetic field. So, we use only the normal component to extrapolate the magnetic field, and then this alpha is corrected by minimizing the deviation between the numerically computed and the observed field on the lower boundary, just the transverse components. So, here are some preliminary results. Actually, I got this result only a week before coming to the heliophysics summer school, so I don't have all the details, but just the initial. So, the top panel shows the extrapolated non-force free magnetic field over the entire domain of this magnetogram. Now, one thing should be noted is that in this location where we saw which was the location for the X-class flare in the initial, in this figure. So, we see a presence of a 3D null-like geometry, so which is zoomed in and shown here. So, this coronal 3D null is also a possible site for magnetic reconnection. So, again we took this non-force free initial magnetic field, and we then evolve it using the same MHD code. So, what we see is that we find reconnections in the magnetic field lines that do occur in the vicinity of this X-type null lines. So, then this can potentially explain trigger for our X-class solar flare. Also, when we look at the top view of this 3D null, we see that the field lines connecting at the other end have this elongated line-like geometry. So, they can possibly explain this flare ribbons that we are seeing in the similar locations in this AA 1600 channel. So, in future, we plan to do a detailed analysis of this reconnections that are occurring at this 3D null site, and this was a non-eruptive event. So, we would like to study the overlying field geometry to explain why there were no CMEs that were produced by such a major X-class flare. Because in general, we know that almost 95% cases, if there is an X-class flare, it is followed with a CME. So, in this case, there were no CMEs. So, we would have to study the overlying field geometry to explain this. And we'll also we have to do a detailed comparison of various observed dynamics in different AIA channels. So yeah, thank you.
Questions? Well, I plenty during the talk.
Is your numerical scheme, does it conserve energy, so the reconnection, the energy given off by the reconnection is put into heating?
So it's a viscous dissipation code, so the total energy does fall off.
Okay, but the viscous heating is self-consistent, like
So the energy decreases.
It's isothermal.
Yeah, it's isothermal, so the total energy slowly decreases. Yeah. Yeah. The initial magnetic field. So what I was doing was I was fitting the initial magnetic field. Uh, this is the initial magnetic field which is fitted with the observed magnetic field by defining a correlation parameter, which is nothing but a point-to-point dot product between the observed and the what we simulate. So we have a set of like thousands of template magnetograms. Each is then compared with the observed magnetogram, and whichever comes as the highest correlation, that is taken as the input field. Yeah. Yeah. Huh. Yes. Huh. So, so actually, these are streamlines of velocity. So initially, we are not prescribing any velocity. So there was no velocity to begin with. But this snapshot is after like 5 time steps in the code. So and so what we are saying is that the initial Lorentz force was such that the flow that was spontaneously generated was such that the velocity streamlines near one of the null points where all of them were like parallel to each other. So the magnetic field lines that have been dragged with this flow would also be all having a parallel direction here. So since all the field lines are parallel to each other, there is no reconnection because we need some angle between the magnetic field lines to reconnect. Whereas the flow that was generated along this X-type null point, so this is sort of bringing the opposite directed field lines. So these field lines have this direction and these are coming from this direction. So they are coming from almost opposite directions here. So they can reconnect near this location. They will reconnect. This is initial, like just 5 time steps before the reconnection will start.
You chose to expand or to express your magnetic, non-force-free magnetic fields in terms of the superposition of two force-free constant alpha.
Yes, linear force.
Well, this is a particular restriction, I suppose. You can really take many different such fields, right?
So,
or is it actually sufficient to take us through?
so you can take. So actually, it depends on the boundary conditions. So when we do this particular extrapolation, so when I was doing the numerical extrapolation thing, so there was a restriction that if you take only superposition of two linear force free field, then or there are two possibilities. You can take two linear force free fields or two force free fields and a potential field. So, but when I ran the simulation, I saw that the coefficient for the potential field was 0 itself when I was getting the best fit. So you can add a potential field, but in principle, these two are sufficient.
And what are the alphas in the two cases? Are they potentially of opposite sign?
So actually, for the numerical case, what I got, they were opposite signs. There was a plus alpha and a minus alpha. Not very high number, very close to 0, but they were plus and minus of the same. So, okay.
Expansion a bit more. Is it, its purpose is to give you in that surface a non-force-free field in terms of two linear force-free fields.
Yeah.
That's all. You don't care at that point what the overlying connection
Yeah,
are.
because we don't have any observations over there. So what we are trying to do is like superpose these two linear force free fields at the lower boundary and trying to.
Is it strictly in a plane that's valid, that expansion, then? Or is it valid over the volume?
No, the expansion is for valid in the entire volume itself.
Yeah.
But since we do not have.
I don't understand how that could be. Something that might mimic things like convection.
No, so.
I know there's a solar thing, revolve with the sun right now.
So actually, there is a general solution that will. So when we solve, we get solutions for both flow as well as the magnetic field, and I can show you that. So, but in this case, we took only the magnetic fields part because we do not have that. Like in principle, the solutions can fit, should be able to fit both the magnetic field as well as the flow simultaneously. And if we have data for both velocity field and the magnetic field, which are reliable. Since we do not have very reliable data for the velocity field, we have taken velocity to be 0, which is better than prescribing something which may not work, because we have the restriction in the code that the flow velocity field should be incompressible. So whenever we are trying to prescribe anything, it was deviating quite a lot. So instead of that, we thought like we'll not prescribe any flow. Let us fit only for the initial Lorentz force, and let the flow be generated spontaneously.
But it's based on the assumption of minimum dissipation, right? So
Yeah.
that has the flavor to me of something that is a relaxation, not driven like convection, but it's a relaxation of high RENRF. So it's a state that might come from.
So it is your minimized.
With very low dissipation.
Yeah. So we are keeping both kinetic helicity and magnetic helicity constant.
Any more questions? Just thank the speaker again then.
Thank you.